Welcome to the presentation, Optimize Oil Recovery with 4D Seismic Data Analysis. My name is Kamal and we will discuss how Paradigm can help you to get the most from 4D data. Let's have a look to this production history chart. As expected, the production increases quickly at the beginning of the exploitation of the field. However, the decreased slope 10 years later is steep. Injection techniques are becoming more efficient and they bring the possibility to extend field lives by many years and extract miscible oil left in reservoirs. In this example, the production has been increased by 30% thanks to CO2 injection. At which cost can we increase this production? The data acquisition can be expensive in order to acquire multi-component data, for example, but also all the complex supply chain that must be set in order to perform injection. If we consider also the complex horizontal drilling and the fact that the rentability of this process is tied to the oil prices, we should better plan well. Unfortunately, we didn't have much impact on the oil price, so Paradigm is giving interpreters tools to get the most from expensive data to better plan wells. In this example, the objective was to increase production by 30% and the analysis has been performed on two vintage datasets from 2000 and 2002. Welcome to CIDERS 14.1. We are going to do the analysis between those two horizons, and we can see here displayed in green the production wells and in orange the horizontal injectors. We visualize in our 3D viewer our two vintage volumes from 2000 and 2002, and a first QC that can be performed is to visually try to see what are the differences between our two vintage volumes. We are going to merge them and apply an on-the-fly subtraction on our two volumes. So of course we need to enhance a little bit the contrast to try to see the zones where the differences are the highest. In black are the zones where the volumes are the same, and when we have colored areas it means that the volumes are different. So we see that in the area of interest the injection has had some effect, but it's really difficult to quantify this way, but visually we already know that we will have some work to do. One of the first steps of the analysis is to check the frequency content of the two vintage volumes. So here is the frequency spectrum of 2000 vintage, and now let's check the frequency spectrum of the 2002 vintage and compare both behaviors. What we see is that the frequency content of the two vintages are quite equivalent. On the high frequency though, we still have some differences and more high frequency content in the 2002 vintage. However, the signal to noise ratio is much better in 2002. On the left we have 2000 vintage section, just on the right 2002 vintage section. We will analyze the signal behavior in a zone where the CO2 injection shouldn't have any impact. So let's have a first look at a cross plot. We see that both vintages are highly correlated, and a more precise look at the statistics show that we have a really high correlation factor between both of them. However, we can try to improve the comparability of those two vintages by using our 4D cross-equalization algorithms. And here, on the third panel of the section, we have the result of this cross-equalization. If we have a look at a crossplot, we see that the cloud of point is more concentrated around the regression line, and the correlation factor is much higher. So by applying this neural network operator, we make amplitude values of our two vintages more comparable by training the neural network in a zone not impacted by the CO2 injection. Let's now check if we didn't modify the frequency spectrum of our cross-equalized volume compared to the initial vintage volumes. In blue we see here the frequency spectrum and the fact that we dramatically increase the signal to noise ratio by using this cross-equalized algorithm. The next step is to structurally smooth the volume to try to eliminate noise content and increase lateral continuity. So here is the deep steer enhanced 2002 vintage, and we see that clearly the signal to noise ratio is increased without messing with the frequencies. What we observe though is that the high frequencies have been removed, so we want to check in the noisy area the frequency of noise, and here in peak we have the spectrum of a really noisy area. Signal to noise ratio is really low, and we see that the frequencies that disappear using the cross-equalization algorithm and deep steer correspond to noise frequency. Now let's have a look to the horizon that have been interpreted in the original vintage. What we can observe is that the horizon is quite spiky and it doesn't really correspond to the structure. So the picking has been really impacted by the noise content of the original vintage volumes. These horizons have been repicked, and we will compare the horizon we obtained picking on the cross-equalized volume and deep seared enhanced volume with the original one. So in black we have the original picking, and with the rainbow color palette we have the picking performed on the smooth cross-equalized vintage volume. What we observe here visually is that the horizon is much smoother. So now let's compare both horizons in a base map view. So here is the smooth horizon, and here is again the spiky horizon picked on the original vintage volume. If we compare them by merging them and applying a subtraction algorithm on the fly, we will see zones where we have colors that correspond to differences between the volumes, and black zones to areas which are quite equivalent. What we observe here is that those spikes clearly appear and give some kind of texture to the horizon. If we want to compare them statistically, what we will see is here on the left the original picking on the raw vintage. In the middle panel, the picking on the cross-equalized and deep-steered volume, and on the right, the difference between those two maps. If we have a look to the histogram, what we see is that the noise that we eliminate corresponds to some kind of white noise with a variance of almost 1 and an average of 0. So we checked that the two vintage volumes were comparable in terms of frequency content. We checked the amplitude values and cross-equalized them and structurally smooth our volume. So now what we want to check is the trace shape behavior between 2000 and 2002. So we use neural network Facies maps based on trace shape neural network approach. What we see here by subtracting the Facies map is that the area in the middle that corresponds to the reservoir doesn't change, and the injectors on the north have had a huge impact on the interval of interest. If we perform a trace shape classification based on relative acoustic impedance difference between 2002 and 2000, we see that the injectors in the north had a huge impact, however the ones in the south don't. So why those injectors in the south didn't have any impact on the production of the reservoir? So we will use proportional slicing, so starting with our top horizon and generating structurally consistent layers, and we will try to see where the CO2 injection from the injectors in the south did go. What we observe using our 40QC tool and comparing cross-correlation maps between the 2000 and 2002 vintage is that in the interval of interest, the CO2 injectors in the north had a huge impact, so the correlation is quite low. In the south, it's not the case. So we will duplicate our workflow and try to see what's happening below the interval of interest. So the interval below that we will look at is located 20 to 25 milliseconds below the top of our interval of interest. So by calculating the same correlation factor but below, what we observe is that the correlation factor between the 2000 and 2002 vintage is much lower in the south now. So it appears that the CO2 injectors had impact below the reservoir area, which let us suppose that we may have a lithology barrier preventing the CO2 to go into the reservoir and improve production. If we have a look at the impact on CO2 injection on the structure, what we observe is that it didn't have much impact. So the structure is not moving because of CO2 injection, and if we have a more precise look at the value of the time shift, we observe that it's less than half a millisecond. So basically, the CO2 injection had effect from the north, but from the south it doesn't enhance the production rate of the wells. We were able to QC our two vintage volumes and be sure that they were comparable between each other. We also checked with the Facies map the fact that the CO2 injection had impact on the north, but on the south they were injecting below the interval of interest. So now we can propose the next injector and maybe sidetrack an existing well in the south and target a layer which is closer to the top of the interval of interest. So we will select our initial injector well, select our target shape, and pick targets on the horizon of interest in order to propose a new well plan. So this will be directly done on our proportional slices that have been used for the Facies analysis. And here we have a drillable well with all the defined constraints that are respected. Those constraints include DDI index, but also dogleg severity, for example. So we here propose a perfectly drillable injector well that could be used to try to optimize the oil production in that area. CIDERS 14.1 has given us the possibility to analyze vintage volumes and raw interpretation in order to plan next injection. Starting from seismic data quality control and going further in the analysis using tools such as cross-correlation and seismic facies maps, we were able to understand better reservoir property changes and therefore deduce why production was not affected by injections in the south. Next well can be planned with confidence. Thank you for your attention.